Today, I'll be presenting my analysis for Company A on determining the most effective material delivery method for a new assembly facility. In the new assembly facility, Company A must determine the best way to transport parts to the line. Kitting and line side stocking are the competing models, and this choice matters because it affects operator walking distance, total production flow, storage needs, error rates, and overall labor efficiency. Choosing the wrong method could create slow production, while the right choice can support lean, stable, and predictable operations. This decision directly impacts Company A's objectives: lean production, high accuracy, and standardized operations. A poor material delivery method creates delays and inconsistencies, but selecting the right one increases productivity, reduces mistakes, and ensures the correct parts are always available at the point of use. I evaluated two alternatives: kitting. Kitting parts are grouped into complete kits and delivered directly to the operator. The line side stocking option, where parts are delivered in bulk and the operator picks compounds during the assembly. Each method offers different advantages depending on the part, complexity, storage needs, and other operational flow. Here is the influence diagram that I created, and this shows the key factors affecting the decision, including labor requirements, characteristics, storage capacity, equipment needs, and error probability. These interaction guides gives us an evaluation of each alternative. So as you can see, your decision it shows you kitting in the line side model and your uncertainties, like material delivery, and then your costs, like your labor costs, your storage requirements. Those are all factors of cost. And the handling of the material is also a factor of cost. And the outcomes is you want to have an efficient system. To understand the current system, we conducted a site observation and a process map to analyze material flow. Collected data on part size, weight, container type, and quality per container. Also use structured criteria to ensure unbiased evaluation so every part was properly observed. For kitting, cost drivers include staging areas, kit building labor, like paying people to actually build the kit, labeling, and specialized equipment. For line side, your cost considerations would be space, allowment, bulk storage, and replenishing costs. And I used a high level cost model to compare cost setup, operating costs, space needs, and error risk. This ensured I captured the full financial impact of each option. These are all examples of kit carts of how things would be delivered to a workstation on a kit. So you have the vertical transportation cart and a combo transportation cart, a door kit cart, and a bread transportation cart. So I created a decision tree model. The decision tree visualizes how different conditions such as part sizes, container quality, and operator walking distance influence model which model performs better. It helped identify where kitting provides high value and where line size stocking is sufficient. So as you look into this decision tree that I made, it would show you the different parts and if it's at an advantage or a disadvantage to using it. So I used a multi attribution decision model with weight scores. Each factor was scored from a 1 to 5, and each factor was weighed was weighed based on its operational importance. This model identifies which method aligns best with production requirements. This is an example of the scoring system that I used and created. The criteria included part size, weight, number of containers, storage needs, process complexity, cost differences, and part commonality. This allowed for consistent scoring across all part families. So as you can see, looking at the diagram, each part has a different weight, and then it has a kitting score and a line side score, and you add it up at the bottom to get what score was better, and then that's how you make your decision. This sensitivity analysis identified three criteria with the greatest influence: line size, storage capacity, operator steps, cost differences between kitting and line side delivery. We found that kitting consistently benefits stations with limited space for heavy and bulky parts. Weight and container type are crucial variables also. To address risk, we use a risk adversary function. This reflects a preference for stability and reduced variability. Utility modeling helps us understand trade-offs beyond cost and highlighted which option delivers more predictable performance. Value of information analysis help determine whether further data collection is worth the cost. The most impactful uncertainties were kit accuracy and the labor learning curve. If the value of information exceeds the cost of performing a pilot test, then we recommend running a controlled pilot to validate key assumptions before fully scaling. We proposed a phase implementation. The first phase would be a pilot project. You set up part families to validate the chosen method, and after that, you'll measure it by tracking kit accuracy, walking distance reduction, and cycle time improvement. 3, you're going to train, prepare operators, and refine standard operating procedures. And then you're going to scale it up. Once stable, expand the processes across the entire assembly line. And this approach minimizes risk and supports smooth adaptation. We consider 3 major ethical and professional factors. The first one would be worker impact. Role changes require clear communication and significant training. Ergonomic safety. Heavy or awkward parts should use appropriate equipment and workstation adjustments. And third, data-driven evaluations. Decisions must rely on unbiased, objective part level data to ensure fairness and accuracy. Based on the overall cost model, sensitivity analysis, and operational scoring, we recommend adopting kitting for part families that benefit from reducing line, storage, and walking distance, and line size stocking where bulk delivery is more efficient. Clear communication, ergonomic planning, and objective data analysis remain essential during this implementation. And as you look at this model here, it would show you that kitting would be the better option. And this is a model that I also made. Key lessons from this project: structural frameworks increase decision consistency, criteria-based evaluation avoids subject or opinion-driven decision making, and the weighted scoring system provides a scalable and defendable decision framework for future material handling questions. Thank you.